Good day, greetings. How are you guys doing today? Welcome to this physics lesson. Today we are looking at the concept pressure. Pressure is a topic that we looked at in grade 9. So I hope you recall some of the concepts related to it. But in this lesson, these are our objectives. By the end of this lesson, we should be able to define pressure is that, recall and use the relationship pressure is equals to force over area. Please know that there's a difference between that P and that rho, right? That symbol that looks like a P also, but it's a Greek letter from the Greek alphabet. That's the letter rho. Say that the pressure beneath the liquid surface is related to the depth and to the density. Okay, to the depth and to the density. We can also look at concepts, issues of maybe buoyancy, how something is able to float. I'm trying to recall, we talked about substances floating and sinking in one of the previous lessons. For some reason I can't recall which one it was, but we definitely talked about density and how if something is, we were using the example of water, and how the substance was more dense than water, then it was going to sink. If it was less dense than water, then it was going to float. And then there was one where the substance was almost the same as water, and would say it's submerged, right? But getting into the crux of it, I hope you still recall the definition of pressure. Pressure refers to the force acting per unit area. And you'd say that pressure is directly proportional to the force applied. To say the greater the force that is applied, the more the pressure, okay, is directly proportional to the force applied, and it is inversely proportional to the area. So you'll find that as force that is being applied increases, then you say pressure is increasing in your calculations. However, if the area is increasing, the pressure is actually reducing. So as you increase the area on which a force is acting, the pressure actually gets to reduce, right? And you would recall maybe a simple example of how if someone pricks you with a pin, right? Pricks you with a pin, okay, like a needle. If someone wants to maybe, when you go and you donate blood, they put a needle into your finger, or I don't know where they put it. But it's very painful. But because the pin has a very, very small area, it means that the pressure that is applied, right, just by applying a very small force, a very large pressure is produced. So the smaller the surface of an object, the higher the pressure that you can exert. Sharp edges exert high pressure as compared to blunt ones, because blunt ones, effectively, the surface area has increased, thus reducing the pressure. It's important for us to know the formula for pressure. Because we are going to use it. We are obviously going to use the formula for pressure and calculating different pressure calculations. I don't think I put a pressure calculation in this lesson, because we are also going to continue with the concept of pressure even in the next lesson. Because we're going to look at pressure in general, then we're going to look at pressure, atmospheric pressure, and it's only at the end of that lesson that I will have us attempt some questions. So take note, please, of the unit for pressure, the formula for pressure, force over area. It's important that you just recall. It's simple stuff, but recall it, remember it. The unit is just taken from the units of the different quantities that are involved. So if pressure is force over area, it implies that the unit is going to be newtons per square meter, because the square meter is the unit for area, right? So newtons per square meter, another name for that is the Pascal. So when we say we are measuring pressure, we measure pressure in pascals. 1 pascal is equal to 1 Newton per square meter, right? Other units of pressure are millimeter of mercury, that mmHg. If you go to your periodic table, you'll find that Hg is the symbol for mercury. And in the next, when you talk about instruments used to measure pressure, I'm sure you remember that we have a mercury barometer, right? We have a mercury barometer, and so when you are measuring pressure, you actually say millimeter of mercury. Then there are bars. You remember those isobars? If you ever saw charts and maps in geography, and then you have isobars, areas with the same pressure. Then ATM for atmospheres. ATM for atmospheres. And here are just some values for you to understand, to say 1 bar is equivalent to 1 atmosphere. But that 1 atmosphere or 1 bar is equivalent to how many millimeters of mercury? And that's 760 millimeters of mercury. 1 bar is equals to how many pascals? 1 atmosphere. That's equal to what? 1.01325 times 10 to the power of 5 kilo. No, just pascals, not kilo. 1.01325 times 10 to the power of 5 pascals, which is the same as 101 kilopascals or 101,000 pascals. So that's just basic information on pressure and the units of pressure. So just pause the video, have a look at these units and the other units of pressure that I use. So say pascals, millimeters of mercury, isobars or bars, it's just bars, and then atmospheres. So just take a minute to go back through the material. Okay, so if we can just watch this short piece, it's going to move from density, right? Density, how you get to calculate density, and then it's also going to have a bit on buoyancy and pressure in liquids. So let's just have a listen.
Lead has a density of 11.3 float. Water has a density of 1 gram per cubic centimetre. Will the wax candle with a density of 0.95 grams per centimetres cube float or sink in water? That's right, the density of the candle is less than the density of water, so it will float. Lead has a density of 11.3 grams per cubic centimetre, and liquid mercury has a density of 13.5 grams per cubic centimetre. What would happen if a block of lead were placed in a beaker of liquid mercury? Pause the video while you think.
Yes, you can pause and just tell us if mercury has a density of 13.5 and lead has a density of 11.3. If you drop lead into mercury, is it going to float or is it going to sink? So answer the question honestly, you'll get the answer like now. But just pause the video, and just by looking at the numbers, I'm sure you must be able to see which one, whether it will float or it will sink.
The lead would float in the liquid mercury. So that's a fairly easy way of explaining why solid blocks float or sink. There is another thing to consider: buoyancy force. All liquids are made up of particles that can slide over each other. When the particles collide, pressure is produced. The pressure in a liquid varies with depth and density and gravitational field strength. In a column of liquid, the water will pour out through the holes in the side of the container.
So this part, I hope we still remember the concept of how pressure increases with depth. How pressure increases with depth. We recall that if you have water in, like that's water in a barrel, right? Water in a drum. So hole that's at the lower point, the water
that pours out would vary.
Sorry, let me just reduce the volume here. The water that's at the lower point, you will find that this one, the water at the lower point, will go a further distance, right? And it's going to have high pressure as compared to the water at the high point, right? The water at the high point is going to have low pressure because we know that pressure increases with depth. So as you go down, whether you're swimming or you're in a swimming pool, or you're in the ocean, the deeper you go, the more pressure that's exerted on your body, right? I think we can also see from the image that is there that for this individual, this toy individual, not a real person, the pressure that is exerted on his feet, it looks like a guy, yes. So the pressure that is exerted on his feet or her feet, if it were a lady, is more than the pressure that is felt at the shoulders, right? Because obviously the feet are deeper in the water than the shoulders. So you see this concept of depth, how pressure increases with depth. This is due to the fact that what? Liquid weight also increases with depth. Liquid weight also increases with depth. And these are also other reasons how depth affects pressure. So go through these, read these, and have an understanding of this concept. So let's just continue with this video and just see where it
Side of the container. The water that pours out of the hole at the bottom of the container travels further than the water that pours out of the hole at the top. This is because the water at the bottom of the container is under greater pressure than the water at the top. The mass of the particles pushing down on the water at the bottom of the container creates more pressure. The deeper the liquid, the greater the pressure. We can use these facts to derive the formula, where P equals pressure, ρ equals density, H equals depth, and G equals gravitational force. Imagine a cuboid submerged in a tank of liquid. The distance from the surface of the liquid to the bottom of the surface of the box is greater than and G equals.
Right, so this formula now for pressure is equals to ρ GH. Right, that's why I was saying this little p, that's ρ, and it represents density. So you have to know the density of the particular liquid, then the gravitational force that is acting on the particular liquid, and then the depth. So when you can clearly see that as h is increasing, that means that whatever is here is going to be multiplied by a bigger number. Therefore, pressure will increase because the height represents the depth. Right? H for height, or h for depth. H for depth. So as h increases, the depth increases, and you are multiplying your ρ g density times gravitational force with a bigger height. And that means that obviously your pressure is going to increase, right? So the density of a liquid also, you should know how then the density of a liquid affects the pressure, right? The denser a liquid is, the higher the pressure at any given depth, and vice versa. If you were to fall into a pool of water, right, or if you were to jump into a pool of water, there is a certain amount of pressure that's going to act on your body, which is effectively normal. But if you were to jump, just think of maybe a pool of pudding. I'm trying to think of something that is thick, something that is viscous, right? Something, if you've ever had, I hope you've had pudding. Okay, think of something else that is, or maybe sour milk. I don't know. Think of something that is thick, but it's a liquid. That if you were to fall into it, the pressure that would act on your body is much greater because of that liquid density. It's actually more denser, right? So it then increases the what? It then increases the density and the pressure which you feel, which is why we're saying pressure is affected by ρ. ρ is usually just a constant liquid density, gravitational field strength, right? So ρ GH. So the density then plays a part in the pressure. If you increase the density, you increase the pressure. If you increase the gravitational field strength, you increase the pressure. Likewise, if you reduce any of those factors, then you're going to reduce the pressure, right? So guys, please go through this material, read up on it. First, we're going to discuss this material in the lesson today. Then we're going to look at atmospheric pressure in the following lesson. Then we're going to answer some questions, okay? So thank you guys for watching the video. Goodbye.